Good afternoon, Algebra 2. Today we are starting a whole new unit, and the first thing in that unit is to talk about exponential growth. Now let's take a second and talk about linear functions for a minute, because those are the ones we're most familiar with. And linear functions, remember when we graphed them, they were always a line. And when you had a linear function, you had always what we called slope. All right, and our slope essentially was our rise over run. So we went up, 3 for every 5 we went over, and then again we went up 3 for every 5 we went over, and so on and so forth. So we always had a slope, and let's say it was 3 over 5, and it was constant the whole time. Our slope never changed. We were always going up 3 over 5. Now when we switch to exponential growth, so we have exponential growth. It's not going to be a line anymore when we graph it. It's actually going to start out like this and then curve upwards. So when we are talking about exponential growth, well, our growth is not the same every time. We would have different sized steps that we would have here. Notice how these are really shallow down here and then it gets steeper and steeper towards the top. It's because the growth is not the same. All right, it's what we now call a growth rate, meaning it's going to grow by a percentage every time, not a constant amount. So let's just take a quick example here. If we start out with 5 bunny rabbits. So we have 5 bunny rabbits, and let's say if we're using our linear model, every day we're going to add 3 more bunny rabbits to it. So then we would have 5 bunny rabbits, then 8 bunny rabbits, and then we would have 11 bunny rabbits, and then we would have 14 bunny rabbits, and then etc., etc. 17 would be next, and 20, blah, blah, blah. Then if we were saying, okay, well we start out with 5 bunny rabbits, but we're going to grow it by 200%, which essentially means we're going to double our bunny rabbits. Well, we start out with 5. If we're doubling this, 5 would then go to 10. And then we've doubled 10, we wouldn't just add 5, we'd have to double 10, which 10 times 2 would give us 20. Look, after 3 days I'm at 20, whereas my linear model, so we'll put an L here for linear and an E for exponential. Whoops, E only has 3 bars. Our linear model would take us 1, 2, 3, 4, 5, 6 days, twice the time it would take me for my exponential. So then our next one, we'd double 20, which would get us to 40, and then we'd get to 80. So as you can see, an exponential growth is a much, much faster growth rate than any linear line could ever be. So that's one key thing you're going to want to remember about exponential growth. Okay, let's take a look at another example here. It says many bacteria reproduce very quickly. Suppose an experiment begins with 300 bacteria and that the population doubles every hour. This is a reasonable assumption over a short period of time. Below is the population at Y after X hours, for X being 0 hours, 1 hour, 2 hours, 3 hours, and then 4 hours. Okay, so as you can see here, we started out with 300 bacteria at no time has passed yet. That's why we're starting at. So this is our initial amount. So initial amount here. And we're doubling, we're doubling every time. So 300 goes to 600, so we multiplied by 2, so times 2. 600 went to 1200, we multiplied by 2. 1200 went to 2400, so we multiplied by 2. 2400 went to 480, which we multiplied by 2 every time. So it's the same factor that we're growing by, but we're not adding anymore. We're now multiplying, so it's going to grow much quicker. And as you can see, this graph, if we connected these lines, oops, sorry, I tried to do that a little more smoothly. But if we connected these lines, it wouldn't, or these dots, it wouldn't make a line anymore. It would make a curve. And if I expanded this over, the 5th hour or the 6th hour, let's say, it would actually go up much quicker, and it would tend to go higher more than it would go out. Okay, so we're going to see that here in the next couple examples of what exponential growth actually looks like. But just know that the whole basis behind the growth here is no longer a constant, let's add 5 every time or add 3 every time. It's something like we're doubling or we're increasing by 30%, because we know percentages are based off of what the initial amount are. Like let's say, for instance, you go on sale, everything's 50% off. Well, that doesn't mean everything that's $50 is $25, and everything that's $100 is going to be $50, and everything that's $70 is going to be $35. So it depends on the price that you start with as to how much you're going to pay. Okay, so it's not constant. It changes with what your initial amount is. All right, so just to get our basics down here, here's your first definition. It's your exponential function, and that is a function f defined by the equation f of x equals a times b to the x power, where a cannot be 0, so you have to start with something, and b has got to be bigger than 0, but it cannot be 1. Okay, and we'll discuss why that is here in a bit. So I've just made this bigger. This is the exact same equation that I took from up here. So I just made it bigger because I want to point out a couple things. So we have f of x, that just means it's a function, equals a times b to the x power. Okay, so your initial amount is where you're going to put a. So for instance, in our previous example, we started with 300 bacteria. So our 300 would go right in here. And then your growth factor, which would be, in the last example, we were doubling, our growth factor would be 2. So we'd put a 2 in here. And so we'd have 300, well, let's just write it out. I guess I can do it over here. So f of x equals, our initial amount was 300, times, our growth factor was 2 because we were doubling it, and then the x should actually always stay as x for right now. So it's 2 to the x power. That's how you know it's an exponential function, is that you have this x power. If you didn't have this, it wouldn't be exponential. Okay, so our initial amount was 300, and our growth factor was 2. And that's the way they will always be set up, just like y equals mx plus b. M was your slope, and b was your y-intercept. Here, a is your initial amount, and b is your growth factor. Okay. Now, why do we have all these restrictions over here? Well, let's look at the a restriction first. They tell me a can't be 0. Well, let's think about what 0 is. 0 is your initial amount. So if we start with no rabbits or no bacteria, and we expect to multiply by something to increase that amount, well, if we multiply anything by 0, what are we going to get? We're always going to get 0. So it'll never really change. You can't double 0. If you double 0, you still get 0. All right, so that's why a is not allowed to be 0. Okay, now let's move over to b. There's 2 restrictions on b, and b has got to be positive, okay, because your growth factor, you think about it this way. If we put a negative number in here, and we took all powers of it, every other power, it would alternate, because, you know, we have even powers. That gives us a positive result here. If we have odd powers, that's going to give us a negative result here. So then it would go positive, negative, positive, negative, positive, negative, which we can't have. That's not growth. That's flip-flopping between positives and negatives. You're never going to get anywhere. You're going to get further and further away from 0, but that's not going to model anything. Okay, so that's why b has got to be bigger than 0. It can't be negative. Okay, why can't b be 1 though? Well, if we put a 1 in here and we take powers of 1, well, let's think about this. 1 to the first power is obviously 1. 1 squared, still 1. 1 cubed, still 1. 1 to the fourth power, still 1. You see a pattern here? If we put 1 in here, would our growth rate ever change? No, it's going to be 1 every time. Which then, if we take our initial amount and multiply it by 1, well, guess what? Anything times 1 is itself, so I would never get past this 300 or whatever it was I started with. It would always be 300. 300 times 1, 300. 300 times 1 again, 300. So that's why we're not allowed to have 1s in here for b either. So there's a few restrictions, but you don't never really run into those kinds of things, or at least you shouldn't. They'll naturally just kind of work themselves out. So I wouldn't worry about it too much. What I would worry about is this right here. This is very important to know this model and what a and b stand for. Okay? So let's see where we can use this model. I'm going to go ahead and pause this video and wait till the next one to show you guys your examples. So please tune in shortly.